In this video, we're going to introduce electrochemical cells. There's two types of electrochemical cells. There's Voltaic cells, and then there's electrolytic cells. But for today, we're going to go over Voltaic cells specifically. So a Voltaic cell is a device which converts chemical energy into electrical energy. And the way that this happens is through a redox reaction. Now, the simplest Voltaic cell consists of two electrolytes in a conducting solution, and that solution is called an electrolyte. Okay, so you need to know what a Voltaic cell is, and you need to know that it converts chemical energy into electrical energy using a redox reaction. So examples of electrolytes would be salt water. A potato, it's referring to the liquid that you find inside of a potato. Lemons or lemon juice, orange juice, or even electrolytes could be found in animal flesh. Okay, so standard Voltaic cells are sometimes called galvanic cells, so you do need to know that Voltaic cells and galvanic cells, they refer to the same thing, and it has various components to it. So the cell is divided into two halves, or in other words, it's called half cells. The redox reaction in Voltaic cells is spontaneous, so that's a key distinguisher in Voltaic cells compared to the other type of electrochemical cells that we are going to talk about, which is electrolytic cells. So you need to know what a Voltaic cell is, and you need to be able to distinguish it from an electrolytic cell. Okay? And one of the distinguishing characteristics is that the redox reaction in Voltaic cells is spontaneous. Now, in Voltaic cells, the OA and RA are kept away from each other, and that's so that you basically force the electrons to flow through a wire to be transferred, and that generates, the movement of electrons through the wire generates an electric current. Okay, so the reaction is spontaneous and it generates an electric current, or it generates electricity. Now, each half cell has all the components present in a half reaction. So with Voltaic cells, you could also, like if you group a whole bunch of Voltaic cells together, you're going to get a battery. Okay, so over here where it says cells versus battery, the difference is that a battery is made up of multiple cells connected together. Okay, so here are the terms that you're going to have to know, both for Voltaic cells as well as electrolytic cells. So you should know what an electrode is, and it's a solid piece of metal where the half reactions occur. The key distinguisher here is that your electrode must be solid. It cannot be aqueous. So electrode or electrodes must be solid. They can't be aqueous. Okay, now the only exception to being a metal would be that you can have a carbon electrode, because even though carbon is a non-metal, it still can conduct electricity. So I'm going to actually rate that as carbon solid. Okay, so even though carbon is a nonmetallic element, it conducts electricity and therefore can be used as an electrode. Okay, so that's just specifying here because this definition does say that electrodes have to be solid pieces of metal. The only exception to that is going to be carbon. Okay, where carbon is a non-metal, but we can still use it. All right, the next definition is a cathode. So cathode is where your reduction half reaction is going to occur. So your cathode is going to be put in the half cell that contains your SOA. So in a voltaic cell, the cathode is the positive terminal. With the anode, that's where you're going to see oxidation occurring. And your anode is located in the half cell that has your strongest reducing agent. Okay, so the cathode and anode, both of these are specific electrodes. So the term electrode is pretty general. It could be talking about a cathode or an anode. Okay, so these are the two types of electrodes. So one's going to be your positive terminal, that's your cathode. The other one is going to be your negative terminal, which is your anode. So because they are specific names for our electrodes, your cathode and your anode, they must be solid. So cathode is the positive terminal, anode is the negative terminal. So you could kind of remember that the cathode is the positive terminal just because if you look at the T in cathode, it kind of looks like a plus sign. So you could think of that as being, okay, that's the positive terminal. All right, so a salt bridge or a porous cup, that is a structure that allows it allows ions to flow between half cells. Okay, anions, those are all your negative ions, and they always flow towards the anode. Okay, so anions go towards the anode. You need to know which electrode, either the anode or cathode, that your ions are flowing towards. So anions go to the anode, cations go to the cathode because they are your positive ions here. Okay, and then the wire, that is the structure that allows electrons to flow from the anode to the cathode. So the electrons, they start at the anode and then they go to the cathode. Okay. All right, so we're going to get into how to label voltaic cells. But one thing before we get into that we need to know is that when the half reaction at the cathode produces a metal, the cathode will build up. Okay, so that reduction half reaction happening at the cathode causes the cathode to build up or increase in mass. Now, how I like to remember that is this little mnemonic device or memory device. So red cat gets fat. So what this means is reduction happens at the cathode and the cathode increases in mass. Okay, so it's very important that you understand that at the cathode, reduction occurs, and the cathode is going to be the electrode that is going to increase in mass if there's any electrode that does increase in mass. Now, going back to our notes here, when the half reaction at the anode involves the oxidation of the metal anode, the anode will dissolve. Okay, so the half reaction at the anode, that's going to be oxidation, and the anode will dissolve. So how I remember that is I say to myself, it's not as catchy as red cat gets fat, but this will have to do, and ox gets thin. So what that means is at the anode, oxidation occurs, and the anode is going to decrease in mass. Okay, so if there's any electrode that's decreasing in mass, that would be the anode. Okay, so rule of thumb, cathodes tend to build up, anodes tend to dissolve. This makes sense when you look at what is happening at each reaction site. So that's going to make a little bit more sense once we actually get into some questions here. Okay, so let's move into steps to labeling a voltaic cell. So first things first, you need to write out a species list. Okay, and then what you're going to do is you're going to use your data booklet to determine the SOA and SRA. Then you're going to write out the SOA half reduction, the SOA half reaction, which is going to be your reduction reaction. So this is going to be the cathode half reaction. Then you're going to write out the SRA half reaction, which is your oxidation half reaction, and that will be the reaction that occurs at the anode. Next, you're going to determine what are your electrodes. So figure out what is your cathode, what is your anode. And remember, our electrodes, whether we're talking about the cathode or the anode, both of them are solids. The cathode is where reduction occurs. So back to red cat gets fat. Reduction happens at the cathode. Okay. Meanwhile, at the anode, that's where oxidation occurs. Okay, so going back to this, and ox gets thin. At the anode, oxidation occurs. Okay, so these two phrases are extremely important for you to memorize because they're very helpful. So if there is not a solid in the half reaction, then you got to figure out what inert electrode. So inert electrodes are typically either carbon or platinum, and you got to figure out which one of those inert electrodes are going to be either your cathode or your anode. It kind of depends on what's being used in the question there. Okay, or what the setup of the voltaic cell is in the question. Another thing that you're going to have to label is the electron flow. So you need to be able to figure out, okay, what's your anode, what's your cathode? Because the electron flow goes from the anode to the cathode along the wire. Okay, so you need to show the electron flow on the wire from the anode to the cathode. You're also going to have to show ion flow. So remember, anions go to the anode, cations go to the cathode. Okay, now when they're talking about the boundary, they're just talking about the salt bridge. So anions, anode, cations, cathode. So the boundary, that just means the salt bridge. or the porous cup, either or. Both do the same thing. So to abbreviate this, anions go towards the anode, cations go towards the cathode. Now, with the electron flow moving through the wire is going to be outside of the beakers, so we're calling this the external circuit. Whereas with the ion flow, that's going to happen in the solutions and across the salt bridge or the porous cup. So this is considered to be the internal circuit. Okay, so in this diagram, we have a copper zinc voltaic cell, and we need to label the cathode and anode, label the direction of electron flow, determine the cathode and anode reactions, and then determine what empirical evidence that would occur for this voltaic cell. Okay, so I'm going to be going through these steps at the bottom of page 45 here. So we need to figure out what is our species list. So let's look here and see what we got. So it looks like we have zinc solid and zinc 2 plus. Okay, so I'm seeing zinc solid right here, zinc 2 plus right there, and ions are always aqueous. Now it looks like we have sulfate and copper, and because these are solutions, that means we also have water present. Okay. We have copper solid, and then if we have copper solid, yeah, we've got copper 2 plus. So that would be aqueous because it's an ion. Okay, so now that we have our species list, we can go to page 7 of our data booklet and just figure out where everything is. So I'm gonna go through the left-hand side to figure out what is my SOA. Okay. So I'm just looking to see, like, I'm looking through the left-hand side, looking through all the chemical species to be like, okay, what do I have? So I do have water, but I don't have this OCl1 minus, so I can't use this reaction. Okay, so let's keep on going. Oh, but I do have copper 2 plus. Okay. Now I have sulfate ions, but I don't have hydrogen ions, so I can't use this reaction right here. Okay, so what else do I have? I've got zinc 2 plus and I've got water, and I think, oh, there we go. We also have sulfate and water, so we can use this reaction. Okay, but I think that's it for the left-hand side. So let's do the same thing for the right-hand side with the reducing agent. So I'm just going through and I'm circling what I have. So I have zinc solid, I have copper solid. And I also have water. Okay, so let's figure out our SOA and our SRA. So for the SOA, I'm putting my finger in the top left-hand corner, and then I'm dragging it down until I hit my first species on the left-hand side. So that means that copper 2+, that is our SOA. So I'm going to label that here. So SOA. And then I got to figure out, okay, what is my SRA, or my strongest reducing agent? So I'm putting my finger at the very bottom right-hand corner, and then I'm tracing my finger up. First species I run into on the right-hand side, where all the reducing agents is zinc solid. So that's going to be my SRA. Okay. So now we can figure out what the cathode and anode is. So looking at my SRA, I'm just arbitrarily going to start there. Okay, and remember, red cat gets fat. And ox gets thin. Okay. So since this is the reducing agents help other things to get reduced, but it itself gets oxidized. Where does the oxidation half reaction occur? It happens at the anode. Okay, so let's just write this out. So zinc solid is the SRA. Oxidation occurs at the oxidation half reaction occurs at the zinc solid. So that tells us that zinc solid is the anode. Okay, so let's look at our SOA. So our strongest oxidizing agent, that is aqueous. Remember, cathodes and anodes, they can only be solid. So just because you figured out your SRA and boom, that was a solid, you always got to double check the states of what you're assigning your SRA and SOA to. Okay, now copper 2+, yes, that's the SOA. Okay, but where is that going to be hanging out? Copper 2+ is going to be hanging out at the copper strip. Okay, so that means the cathode is the copper strip, because that's the solid version of our copper 2+ ions. Okay, so copper 2+ is the SOA. Okay. Reduction occurs. So if we're talking about reduction, red cat gets fat. Reduction happens at the cathode. So cathode is copper solid. So that's going to be that. Okay, so that's question number 1. We labeled the cathode and the anode there. Okay, so step 2 is label the direction of the electron flow. So reminder, electrons start at the anode and go to the cathode along the wire. Okay, so the electron flow, we're going to write on the wire, and we're going to go from the anode, which is our zinc strip, and goes to the cathode, which is the copper strip. Okay, So that's step 1 and 2 done. Now step 3, determine the cathode and anode reactions. So this is based off of what you figured out was your SOA and SRA. Okay, so down below here, since it talks about the cathode half reaction first, that's where I'm going to start. Okay, so remember, red cat gets fat. So this is going to be our reduction half reaction. Okay, so that's going to belong to our SOA. Because remember, strongest oxidizing agent helps other things to get oxidized, but it itself gets reduced. Okay, so I'm going to check out this copper 2+ reaction in my data booklet. So where was it? It was right here. So because I'm writing the reduction half reaction, I'm starting from the left-hand side and I'm writing this going to the right. Okay, so copper 2+ aqueous plus 2 electrons gives us copper solid. Now for the anode half reaction, so anox gets thin, so this is going to be our oxidation reaction because oxidation happens at the anode. Okay, so I'm going back to my SRA and let's figure out, okay, what was that reaction with our SRA? So this is our SRA, and how I'm going to write this reaction, I'm going to start from the right and go left as I'm writing it. Okay, so we're starting at zinc solid and we're producing zinc 2+ and 2 electrons. And I'm lining up these reaction arrows here just to make it easier to get the net reaction. Remember, you need to be using reaction arrows. Do not write equal signs. So zinc 2+ aqueous plus 2 electrons. Okay, one other thing that I want us to start writing out, so this is a little bit extra to the question here, but one thing you're going to want to get familiar with is using these voltages that are assigned to each reaction here. Okay, so with our cathode reaction, we had a voltage of 0.34. Okay, and since we wrote this reaction from left to right, we can use this. If we write the reaction backwards, then we have to flip the sign on the voltage. Okay, so for right now, the cathode reaction, since we wrote it from left to right, we can use 0.34. Okay, but please note I am adding a bit to this question that's here. So the question is, what's the voltage on the battery? Okay, now since for the anode half reaction we wrote that backwards, okay, so we wrote it from right to left, that means we got to flip the sign on this negative 0.76. So we got to flip it from negative 0.76 to positive 0.76. Okay. Now let's add up both of these reactions and then we'll add up the voltages so we can get the net voltage. All right, so remember when we're adding up half reactions, your goal is to make it so that the electrons cancels out. Now, since we have the same amount of electrons on opposite sides, these are going to cancel out already. We don't need to multiply one half reaction or the other. Okay, so now we can just go into the net reaction. So copper 2+ aqueous. Remember always to write the charges when applicable as well as the states, plus zinc solid gives us copper solid plus zinc 2 plus aqueous. Okay, and then for the voltages, because both of them are positive, we're just going to add them up. So what that's going to look like, 0.34 plus 0.76, we get 1.1. But since we're adding, we need to apply adding and subtracting sig-dig rules, which are different from multiplying and dividing sig-dig rules. So adding and subtracting sig-dig rules just tell you to go to the least amount of digits after the decimal. And since both of these numbers have I should have said the least amount of significant digits after the decimal there. And since both of these numbers have 2 significant digits after the decimal, my final answer needs to have 2 significant digits after the decimal. Okay. So don't forget about sig-digs. So sig-digs I'm going to abbreviate to SD. Okay, so we determined the cathode and anode reactions, and one thing I'm actually going to do, let's just add in here cathode reaction, so that's the reduction reaction. Anode half reaction, that's the oxidation one. Okay. So, empirical evidence. What are we going to see when this battery is operating, essentially? Okay, so this is a very simplistic battery, and it's made up of 2 half cells. So, this would be where 1 half cell is. So, let's use a different color here. But it's a very simplistic battery, effectively. Okay, so in order to determine the empirical evidence, what empirical evidence is, if you look at this, what are you going to see? Okay, so part of that can be figured out just by checking out your net reaction. So looking at the products of my net reaction, I see that copper solid is going to be produced. So since the copper strip is our cathode, that means that red cat gets fat. Our cathode is going to increase in mass. And you know what? I'm going to say the cathode, which is copper solid, okay, and looking again at my net reaction, I'm noticing that zinc solid turns into zinc 2 plus. So that means the amount of zinc that we have is diminishing, okay? And what's made up of zinc solid? Well, that's our anode. So our anode, which is zinc solid, will decrease in mass. Okay, you could also say that you'll see the voltmeter have a reading of 1.10. Okay, so if you're wondering where that 1.10 reading comes from, it comes from the voltages of your cathode and anode reaction adding up. Okay, so sometimes we don't always want to draw out these huge drawings. By the way, you do have to be able to draw these types of drawings showing both of the half cells, the salt bridge, the voltmeter. So the voltmeter is this thing, the wire, the electrode, so on and so forth. So you are expected to be able to draw something like this. Okay, but sometimes like those are a bit of a hassle to draw out. Okay, so instead of drawing an entire voltaic cell, cell notation can be used. Okay, so over on the left hand side here, so to the left of these double lines, so the double lines just mean that this is the salt bridge or porous cup. And as a reminder, the salt bridge or porous cup, that's necessary for voltaic cells because it lets the ions move between the half cells. Okay, but this over here that I put a box around, this is one of your half cells. Okay, and maybe I'll use a different color here. So, what if there we go. So I'll adjust this here. We'll make that pink. Okay, and then the other half cell is right over here. Okay, so notice here that the electrodes are put at the end. Okay, and keep in mind the cathode isn't always on the left-hand side. The anode isn't always on the right-hand side. Okay, you can put your cathode on either the left-hand side or the right-hand side. Okay, but wherever you do put it, you need to make sure you put the electrolyte that your cathode is in with the cathode. For the anode, whatever side you put it on, you have to make sure that the electrolyte or the solution that the anode's in goes where the anode goes. Okay, so the electrode, remember that is the solid. The electrolyte, that is the solution that that certain electrode is in that one particular half cell. Then over here, let's write that out. So the electrode is a solid. The electrolyte is the solution. So the aqueous part. Okay, so why are there lines in between the electrode and electrolyte? Well, that's just to show that there's a boundary, or to show that the electrode is in a different state than the electrolyte. So the line is there because the electrode and electrolytes are separate things, but the electrode is placed in the electrolyte. Okay, so if I was to go back to this drawing here, and let's say the electrode we're talking about is the zinc strip. Okay, so the cell notation we were just talking about on the left-hand side, just for giggles here. Okay, so this would be our electrode, and notice how it's sitting in this solution. That solution is called the electrolyte. Okay, and similarly for the other half cell here. Okay, so the electrode being placed in the electrolyte for our drawing here, if we were trying to represent the cell notation for this one, copper solid would be the electrode, and this solution would be the electrolyte. Okay, so let's look. Actually, you know what? I said something that's important, but I didn't write it down, so let's write it down. Okay, so I said anodes don't necessarily always go on the left side, cathodes don't always go on the right side. You have to figure out what your anode and cathode are. Okay, so let's look at an example here. So we've got a silver electrode, which right now we don't know if it's a cathode or anode. But this electrode is sitting in a solution or an electrolyte solution of silver nitrate. And then we have our salt bridge or porous cup, which separates this half cell from the other half cell. Okay, and we have our other electrode, which is copper solid, sitting in a solution, an electrolytic solution of copper nitrate. And there's actually a little error here. So let's just correct this. So this should be copper 2 nitrate, aqueous. There we go. Okay, so we need to figure out what's our cathode reaction, what is our anode reaction. So first things first, write out a species list. So this makes it a bit easier. So okay, we've got silver, and since silver nitrate, we know that's a solution, so it should dissociate. So that means we've got silver 1+ ions, nitrate ions. Since we've got solutions, that also means that we've got water present. Okay, and then we've got copper 2+, aqueous, because again, this is aqueous and it's an ionic compound, so we can assume that it dissociates. And I'll just write nitrate again here, just to make sure it's covered. And then we've got copper solid. Okay. So we've got our species list from both half cells. Let's figure out our cathode reaction. Now, in order to do that, we need to figure out, okay, what is our SOA? What is our SRA? So I need to clean this up a little bit. Okay, so I'm going to start with the OAs. So I'm just looking through the left-hand side to see what oxidizing agents that I have here. Okay, so just a heads up, AU, that's not the same thing as silver, that's gold. Okay, now we do have nitrate, but we don't have hydrogen ions. It's not acidified, so we can't use this reaction here. But we do have silver 1 plus. What else do we have? We have copper 2 plus. Just a heads up, nitrite, which is what NO2 is, NO2 1 minus is not the same thing as nitrate, which is NO3 1 minus. So we can't use this one either. We do have water. And I think that's it. Okay, let's just look through our reducing agents and see what we have here. So I have silver, but I don't have iodide ion, so I can't use this. Same with this reaction. I don't have bromide ion, so I can't use this one either. Okay, I've got copper solid. I've got silver solid. And I've got water. Okay, so looking at this for the SOA, put my finger in the top left-hand corner. Boom, silver 1 plus is the SOA. So I'm going to write this reaction for my cathode reaction. Okay, so remember cathode, that's where reduction occurs. And the cathode is the solid that is with your SOA. Okay, so that reaction was silver 1 plus aqueous plus 1 electron gives us silver solid. Okay, so all I was doing was I was writing this reaction from left to right here. All right, now we got to write our anode reaction. So our anode reaction, that's going to be our oxidation reaction, and the anode is the solid with the SRA. So our SRA, I got to start in the bottom right-hand corner. So put my finger right here, scroll it up. Now the first thing I hit is copper solid. So copper solid is our SOA, and I need to write this reaction backwards, so from right to left. Okay, so to get the net reaction, I need to make sure that my electrons cancel out. So that means I need to find the lowest common multiple, which is going to be 2. So that means I have to times everything in my cathode reaction by 2. So that's going to be 2 silver, 2 electrons, 2 silver solid. So the most common mistake in this step is forgetting to multiply absolutely everything by whatever you're multiplying by. Okay, but now my electrons, they cancel out. Nothing else does, so I can move on to the net reaction here. So that's 2 silver ions plus copper solid goes to 2 silver solid plus copper 2 plus ions aqueous. So remember to include charges where necessary and states for everything. All right, so inert electrodes. An inert electrode is an electrode, so it's a solid metal, usually, unless you're talking about carbon, that does not react. That's why it's called inert. Inert means it doesn't react. So they are used when there is no metal that corresponds to the ion or when using gases. So common inert electrodes are going to be carbon, so carbon solid, and platinum. So that's PT solid. We're saying solid because electrodes are always solid. Okay. So this next statement says you can only replace something in the cell if it's not the SOA or SRA, and inert electrodes are never the SOA or SRA. Okay? They're usually in the solution that contains either the SOA or the SRA. Kind of just depends on the question setup. Okay? So what this, you can only replace something in the cell if it's not SOA or SRA, that just means you can only replace something if it's not the SOA or SRA and not affect the operation of the cell. All right, so example question. So here's our inert electrode. Okay, so our carbon solid electrode, we don't know if it's a cathode or an anode, but it's in a solution with hydrogen ions, and it looks like potassium dichromate. Then we have iron 2 chloride for a solution that our iron electrode is in. Okay, so we're given our cathode reaction here. So that belongs to the SOA. The anode reaction, we've already been given this. That was iron. So keep in mind, because carbon is in the electrolyte solution that the SOA had, that means that carbon is going to be our cathode. Okay, because it was sitting in the solution that contained the SOA. Okay, so there's a small error with the net voltage there. So let's look at these two reactions for the cathode and anode, and let's just correct that. So let's clean this up. Okay, so the cathode half reaction is right here. So that has a voltage of positive 1.23. So the SOA reaction, that's a reaction that you write the voltage as is because you wrote that reaction from left to right. Okay, but the anode reaction, that's going to be involved with our SRA. Let's just find that. So it had iron solid in it. So it's right here at negative 0.45. Okay, so since this reaction was written backwards, we got to flip the sign on the voltage from negative to positive. So it's going positive 0.45. So if you add those up, you get 1.68 volts. So that's why there was an error with the net voltage here. Should be 1.68 volts. Okay, so for the rest of it, it's just taking you through all the steps with labeling this this battery, okay, or the two half cells. So what you will be expected to do is list your cathode reaction, your anode reaction, figure out the net reaction, figure out what is your cathode, what is your anode, the net voltage, as well as say, okay, what are your anions, what are your cations, okay? So the example that I'm going to do here is going to be this one here. Okay, I was looking at 102, but it looked a little bit similar to this example that was just written out here. Okay, it is a little bit different though. Okay, so we've got our 1/2 cell and then we have our other half cell. Okay, so we've already got our species list here. We just need to figure out what is our SOA and our SRA. Okay, and we got to do steps A to H here. Okay, so we're going to want to figure out what our SOA and SRA are. Okay, so we've got silver 1+ ions, cadmium 2+ ions, cadmium, and we also have water. So I'm going to write water over here. Okay, so this is our species list. Okay, so if I look at all of these reactions here, okay, I'm going to figure out, okay, what is my SOA? Given that we have silver 1+, water, cadmium 2+ ions, and cadmium solid. So looks like we've got silver here, and that is our first substance that we run into on the left-hand side. So silver 1+, that is our SOA. So that's going to be the reaction that happens at our cathode. So cathode reaction, that's going to be silver 1+ plus 1 electron gives us silver solid. Okay, so remember that the cathode reaction, that's going to be your reduction half reaction. Meanwhile, your anode reaction is going to be where oxidation occurs. Okay, so on this diagram, I'm also going to make sure to label everything here. Okay, so arbitrarily, I'm going to say that this one right here, that's our silver solid strip. So that's going to be our cathode. Oop. Okay, so if the silver solid is the cathode, that must mean that the cadmium is going to be our anode. Because you can't have two cathodes and two anodes. You have one of each. Okay, so where am I going to write this? I think I got to write this over here. Here we go. Cadmium solid. So I'm going to write, just so it's neat, anode. That's the cadmium solid. And I'm going to make sure that C actually looks like it's capitalized. Okay. So looking at the redox table here, okay, I'm keeping all of my species just in my mind, and I'm saying, okay, what do I run into first? Now, if keeping your species list in your mind is tough, because sometimes those species lists get long, you can go through each species and circle them or point them out with a sticky note on this table here to help you out. Okay, so I'm running into cadmium first. So that's going to be my SRA. So my anode half reaction, I'm going to write this backwards, starting at cadmium solid, going to cadmium 2+. Okay, so our net reaction here, we got to make sure that our electrons cancel out. Okay, so the lowest common multiple between 1 and 2 is going to be 2. So then I got to times everything in my cathode reaction by 2. So now my electrons cancel out. So now I can write my net reaction. So 2 silver plus cadmium solid gives us 2 silver plus cadmium, 2 plus aqueous. Here we go. Now for the voltages for both of these half reactions. So the reaction that I wrote going from left to right, that was that silver reaction, so positive 0.8. And then the cadmium one, we wrote that going backwards, so I got to flip that negative sign into a positive sign. So let's write that out. So the silver one was at 0.80 volts, and then this one, since we wrote it backwards, I'm flipping the negative 0.4 into a positive 0.4. So that means that when we're adding these up, that's going to give us 1.20 volts. So I already took sig digs into account there. So the net reaction, or sorry, the net potential, so E net potential, that is 1.20 volts. Okay, what else do we have to do? So we got our cathode reaction, anode reaction, net reaction. We labeled the anode and the cathode. Those are always going to be the solids, never aqueous. We already wrote out the net electric potential. Now we just need to write out our anions and our cations. So remember, anions are your negative ions, cations are your positive ions. How you can remember your positive ions are the cations is look at the T, looks like a positive sign. That's how you know cations are the positive ions. Okay, so let's write those out. Cations. What do we got? We've got silver, 1 plus. We've got cadmium, 2 plus. And that's it. For the anions, there are none. Done. All right, so we've gone through all the steps A through H. That's how you should be doing these types of questions. Okay, and even if you have an inert electrode in these cells, you still need to identify the inert electrode as either an anode or a cathode. And what's going to determine whether it's an anode or a cathode is going to be what solution it sits in. So if it's sitting in a solution that contains the SOA, so if this is sitting in a solution that contains an SOA, that means this is a cathode. Or if this carbon electrode, which is an inert electrode, is sitting in a solution that has your SRA, then it's going to be the anode. Okay, so I don't really have a whole lot of room on this page, so I'm going to write a little note on the next page that's important, so it's what I'm already saying here. So, 4 inert electrodes. So those are your carbon solids or platinum solid. Remember, electrodes are always solid. And you know what? I'm also going to write this vague enough so that it applies to like non-inert electrodes as well. So whatever solid, so that's important that we're talking about solids when identifying electrodes. So when identifying electrodes, so your cathode or anode, whatever solid is in the electrolyte solution that contains the SOA is the cathode. And whatever solid, when you're identifying your electrodes, whatever solid is in the electrolyte solution that contains your SRA is going to be the anode. Now, granted, sometimes your SRA, when it's solid, is the anode, but I'm trying to make this vague enough so it applies to identifying any electrodes, whether you're talking about just regular electrodes, regular solid electrodes, I should say, or inert electrodes.